Hello everyone, my name is Dr. Ranjith Kumar Gatla. I am working as a Associate Professor in Electrical and Electronics Engineering Department, Institute of Aeronautical Engineering, Hyderabad. Today, I am going to explain the single phase half wave bridge thyristor rectifier with R load and RL load. So this topic is from module 2. So this is the first topic in the module 2. These are the different topics which I am going to cover in module 2. So the module 2 is phase controlled rectifiers. In this module, I am going to explain the first topic is about the single phase half wave bridge thyristor rectifier with R load and RL load, so which is also called as highly inductive load. And the next topic is single phase full bridge thyristor rectifier with R load and again with heavy or highly inductive load. And the next topic is the derivation of average load voltage and load current. So which means we need to analyze the performance of the single phase half wave bridge rectifier as well as the full bridge rectifier by deriving the average load voltage and the load current, and also I will explain how to derive the RMS voltage and as well as the RMS current in each case, which is the single phase half bridge converter with R load and as well as the single phase half bridge converter with RL load. So similarly for the full bridge rectifier with R load and RL load. And the next topic that we are going to discuss is the effect of freewheeling diode and as well as the effect of source inductance on the characteristics of the rectifier. So again, the effect of freewheeling diode and the effect of source inductance that we will discuss for both the rectifiers which are half wave bridge rectifier and as well as the full bridge rectifier. And next topic is the three-phase full bridge thyristor rectifier with R load and highly inductive load. So in this case, the first topic which is about the single phase and the next is about the three-phase. In the three-phase, we are going to discuss only the full bridge thyristor rectifier with R load and heavily inductive load, as well as we will discuss the three-phase half bridge thyristor rectifier also we will discuss. And the next, the last topic in the module 2, which is the dual converter. And in this dual converter, we will discuss two modes of operation. One is the circulating current mode of operation and the second one is the non-circulating current mode of operation. And finally, we will solve some numerical problems based on the derivations and the mathematical modeling which we discussed in the topics which are included in module 2. Then now we are going to discuss the first topic, which is the single phase half wave bridge thyristor rectifier with R load. So before going to that, let me explain what are the course outcomes and how it matches to the Bloom's taxonomy, which is the knowledge level. Okay, so as we know, there are different Bloom's taxonomy levels. So here, when for the module 2, the CO4 and CO5, that is the course outcome 4 and 5. So the course outcome 4, it states, demonstrate the working principle of thyristor based AC to DC converter and calculate the performance parameters under various load conditions. So which means here we will discuss the different types of thyristors based AC to DC converters. So after completion of this module 2, so we will able to demonstrate the working principle of thyristor based AC to DC converters. So which are the different AC to DC converters, which are the single phase as well as the three phase, and with different loads which are with R load and RL load. And also we will calculate the performance parameters under various load conditions. The performance parameters are nothing but just now we have discussed, which are like average load voltage and average load current, as well as the RMS load voltage and the load current with various load conditions. Because as we know, if we change the load, then the RMS voltage value and the RMS current value will also change. So that we can also able to calculate. When coming to the course outcome 5, which is examine the effect of source inductance on the rectifier output while assessing the performance of the converter. So here we will also able to examine the effect of source inductance on the rectifier output while performing the or while assessing the performance of the converter. So the performance, again, how we will assess based on the performance parameter values as well as based on the output waveforms, which we can also call it as the characteristics of the particular rectifier with a particular load condition. And when coming to the course outcome 4, which is the understanding level, the knowledge level of the course outcome 4 is, which is understanding. Of course, that we will just understand what is the working principle and how to calculate the performance parameters. And when coming to the course outcome 5, which is about the analyze. So, which means we should analyze the characteristics, or we should analyze the output of the rectifier based on the performance parameter as well as the characteristics when the source or when the inductance is included in the source. That we will able to analyze. This is about the course outcomes. And the next one, how these course outcomes are mapped with the POs and PSOs. So as we know, we are having totally 10 program outcomes and as well as 3 program specific outcomes. So here, how we are going to achieve these program outcomes with the course outcomes. So here, these 3 program outcomes are mapped with the module 2, okay, which means we are going to achieve the program outcomes by using the course outcomes, which are CO, especially with respect to the module 2, which are CO4 and CO5. So these are the 3 program outcomes and as well as the 2 program specific outcomes, which are mapped with the module 2. And how we can see here, the program outcome 1, here it is about, you can see the keywords like the engineering knowledge, which is apply the knowledge of mathematics, science, engineering fundamentals, and an engineering specialization to the solution of complex engineering problems. So here, we already discussed the different course outcomes, which are CO4 and CO5. In the CO4, if you look at here, we will calculate or we will able to calculate the performance parameter under various load conditions. So if you want to calculate the performance parameter, so we should know or we should have the knowledge of mathematics, okay, and engineering fundamentals. So that's why here the CO4 is mapped with the PO1. And as well as when coming to the PO2 is problem analysis, like identify, formulate and review research literature and analyze complex engineering problems, research sustained conclusions using first principle of mathematics, natural science and engineering sciences. So again, here also this PO2 is mapped with CO4. And next, the PO3, this is the design and development solutions, which is design solutions for complex engineering, which means, there are different rectifiers, different types of rectifiers. So based on our application, so we will design the rectifier. So that will comes under the PO3, which is the course outcome 5, okay, so which is mapped with PO3. So similarly, the program specific outcomes, which is PSO1 and PSO2. Then here you can see in this tabular column, so here clearly indicating, so the which course outcome is mapped with which program outcome and which program specific outcomes. So if you see here, the CO4 is mapped with all 3 program outcomes and all the 2 program specific outcomes. But the CO5 is mapped with only the program outcome 1 and 2 and only the program specific outcome 1. Then coming to the main topic, which is the phase controlled rectifier. So what is phase controlled rectifier actually? So here the phase controlled rectifiers employing thyristors as rectifying elements are used to convert the AC input voltage into controllable DC output voltage. So the function of the rectifier is, if we can say in simple words, the function of the rectifier is it will convert the AC input voltage into the DC output voltage. That is in simple words we can say. But when coming to the phase controlled rectifier, it is a controlled rectifier. So which is nothing but the output should be controllable. So that's why here the phase controlled rectifier is nothing but it is used to convert the AC input voltage, which is the AC input, which is the fixed voltage, into controllable DC output voltage. So the output to DC voltage can be controllable. That is the phase controlled rectifier. Of course, here you can see the rectifying elements we are using here are the thyristors. There are different semiconductor devices like the thyristors, IGBTs, MOSFET, BJT, GTO. So we can use any kind of semiconductor device in the phase controlled rectifier. But according to our application, again, the rectifying elements which we are using in the controlled rectifier is vary. So here in this total module, we are using the rectifying elements are thyristors. Of course, that is the controlled rectifiers, but there are some uncontrolled rectifiers also there. So in that case, we will use the other the switching devices, which are diodes, that we will discuss in later. Next, here you can see the typical AC to DC converter schematic. Actually, in this module, we are going to discuss about the rectifier. So let me show you the general configuration of the rectifier. So this is the general configuration of the rectifier. But actually, in practically, this rectifier is not enough to convert the AC supply or the AC voltage to the controllable DC voltage, because we need some other devices also. So practically, so this configuration is like the typical AC to DC converter schematic. So here you can see initially we are giving the AC supply to the transformer. So as you know the function of the transformer, it can step up and step down the voltage. So because here before the rectifier we are giving AC supply through the transformer. Why we are giving AC supply to the transformer? Because here again the rating of the rectifier may be different based on the application. Suppose if we use in the low power application, then the rating of the rectifier is very low. So it may be it is not in a position to hold the high voltage. Like as we know, if it is a single phase, that is basically the standard voltage is about 230 volts. But this rectifier may not need the 230 volts, because if you give the 230 volts, so because the thyristors we are using in this rectifier may be the low rating thyristors, so the thyristors may get damaged. So that's why the input also we should take care. So how much voltage we are giving to the rectifier. So that's why here we are using the transformer. So by using the transformer, we are just stepping down the voltage, and that step down voltage we are giving to the rectifier. Then after that, after the rectification, we will get the DC voltage. But after the rectifier, the voltage which we are getting, which is DC, is not a constant. But actually it should be constant DC like this. But here, as you can see, this is not a constant DC. This is a pulsating DC, which is nothing but here the output DC voltage waveform containing some harmonics, okay, or the ripple content. So we should eliminate the harmonics and ripple content from the output voltage waveform. So for that purpose, we are using the filter here. So by using the filter, we can reduce the ripple content in the output waveform. Of course, by using the filter, we cannot eliminate, we can just only reduce. So then you can see after the filter, you are getting the waveform, this one. So initially the input is this, and after the rectification, we will get the pulsating DC. Then after the filter, we are getting, of course, the ripple content reduced waveform. Then after that, we will give to the voltage regulator. So this will regulate the output voltage. So then according to the load requirement, we will give the output voltage to the load. Then after the regulator, we will get the constant DC that you can see here in this waveform. So let me consider this is the 4. Like this is the practical schematic in case of the rectifier. Then what are the different applications of the phase control rectifiers or the rectifier? So we can simply say the applications, when coming to the applications of this rectifier, wherever the application need the input as a DC, in all these applications we can use the rectifier. So wherever we need the input supply as a DC, so in those all applications we can use these rectifiers. Here I have mentioned some applications, but not only these, there are so many applications for these rectifiers. So I have mentioned some of them. One is the traction system working on DC. In the traction system, as we know, some DC motors they used. So for that they need a DC supply. So for that we can use this rectifier to convert the AC to DC to run that motor. Then the second application is electrochemical and electrometallurgical processes. So electrochemical is nothing but like we can call it as a battery applications. So if you want to store the energy in the battery, or if you want to charge the battery, we should give the DC supply. So there also we can use the rectifier. And the power supplies, then the portable hand tool devices, like some portable hand tool devices will run on the battery. So we need to charge the battery before using those devices. The best example is like our mobile. If you can see, if you want to charge the mobile, we will use the charger like the adapter. So inside the charger or the adapter, you can find the same schematic which we have seen before. Like there you can find a transformer, and there you can find a rectifier circuit, and there you can find a filter, there you can find a voltage regulator. So these all devices you can find in a small charger, the mobile charger. So that is one of the best example for the rectifier applications. And also we will use the high voltage DC transmission systems, HVDC. So these are the different applications of the rectifiers. Next, when coming to the different types of rectifiers. So basically there are different, the basic classification of the rectifier is, like you can see, these are the basic 3 different types of rectifiers. One is the uncontrolled rectifier, next is fully controlled rectifier, and the next one is the off controlled rectifier, which is also called as the semi controlled rectifier. So based on what parameter we are classifying these rectifiers, which is based on the output, whether the output is controllable or not, or whether it is fully controlled or we can control only some extent. So based on the output, the controllability of the output, so here we are classifying 3 different types of rectifiers. When coming to the uncontrolled rectifier, in case of uncontrolled rectifier, which means the output is not controllable DC voltage, which is the constant DC or uncontrolled DC voltage. We can also not say constant, it is uncontrollable. We cannot control the output DC voltage. So in these uncontrolled rectifiers, the rectifying elements which we are used are the diodes, because as we know, the diodes are uncontrollable devices. So we cannot switch on, which means we cannot control the on and off of the diode. So that's why in case of uncontrolled rectifiers, the rectifying elements we use the diodes. So the input is fixed AC and the output is also almost the fixed DC. We cannot control. And when coming to the fully controlled, in case of fully controlled rectifiers, we use the rectification elements are thyristors. Because as we know, the thyristors are the controllable switches. Of course, even the thyristor is also, we can call it a semi-controlled switch, because we can only control the switch on, but we cannot control the off. And by using the fully controlled rectifier, we can control the output DC voltage. And in case of the semi-control or off-controlled rectifiers, so here the the rectifying elements, we use a mixture of diodes and SCRs. So that's why this is a semi-control or off-control, which means some extent only we can control the output DC voltage, not fully control. Only some extent we can control. So based on the controllability of the output, whether we can control or not, or if we control, then how extent we can control. So based on these parameters, we are classifying the rectifiers as a uncontrolled rectifier, fully controlled rectifier, and the off-controlled rectifier, or we can also call as semi-controlled rectifier. We can also further classification of these rectifiers. Here, first classification is based on the input supply. So which means whether we are giving the input supply as single phase or the three phase. If we give the single phase, then that is a single phase. If we consider the full controlled rectifier, so the full controlled rectifier, again based on the input, we can classify into two categories. One is the single phase full controlled rectifier and the three phase full controlled rectifier. Similarly, in case of uncontrolled rectifier also, the single phase uncontrolled rectifier and the single phase or the three phase uncontrolled rectifier. Similarly for the semi-control also. That's why I told you those three are the basic classification of the rectifier. Those are uncontrolled and fully controlled and off controlled or semi-controlled. And next classification is based on the quadrant operation. So basically, as we know, there are 4 quadrants. So here let me consider, this is on x-axis I am taking the positive voltage and y-axis I am taking positive current. So which means here it is the negative voltage and the negative current. Let me consider this is the first quadrant and this is the second quadrant and this is the third quadrant and this is fourth quadrant. So first let me discuss about the one quadrant operation or one quadrant rectifier. So the one quadrant rectifier is nothing but the rectifier will operate only in the first quadrant. The rectifier which will operate only in the first quadrant, which is nothing but the rectifier output voltage and current always positive. The rectifier output voltage and current which is always positive, then that rectifier is called as a one quadrant rectifier. Similarly, coming to the two quadrant rectifier. So in case of two quadrant rectifier, suppose let me consider in the one quadrant the voltage and current should be always positive, V and I. And in case of two quadrant, the current is always positive, but the voltage may positive or the negative, because up to some extent we may get the positive voltage and maybe after that we may get the negative voltage. So in this case, the rectifier is called as the two quadrant rectifier. So the two quadrant rectifier, which means the voltage or any one of the parameter. It can be voltage or it can be current. Okay, so here I am just considering the voltage, because anyway in the two quadrant rectifier, okay, so the voltage will be positive and negative we will get, but the current is always positive. So that is a two quadrant rectifier. And when coming to the four quadrant rectifier, which means the rectifier that we can able to operate in all the four quadrants, which means it can be, the voltage can be positive or negative, and the current is also can be positive and negative. Suppose if we will get the output voltage and current both are positive, output voltage and current both are positive, then it will be operated in the first quadrant. And if the voltage is negative and the current is positive, then it will be operated in the second quadrant. And if both voltage and current are negative, then which means it can be operated in the third quadrant. And the fourth quadrant, suppose if the voltage is positive and the current is negative, then we can say it can be operated in the fourth quadrant. So a rectifier which can operate in all the four quadrant is called as a four quadrant rectifier. Then what are the single quadrant rectifier and the two quadrant rectifier and the four quadrant rectifier? Because already we are having the basic three classifications, which are uncontrolled and fully controlled and semi-controlled or the half controlled. So the one controlled rectifiers are the uncontrolled and semi-controlled rectifiers are also called as one quadrant rectifier or the single quadrant rectifier. When coming to the two quadrant rectifier, the full controlled rectifiers are also called as the two quadrant rectifier, which means by operating the full controlled rectifier or the full control rectifier, we can operate in the first quadrant as well as in the second quadrant. Then when coming to the fourth quadrant, the dual converter, it can be operate in the four quadrants. So the dual converter we can also call as a four quadrant rectifier. This is the different types of rectifiers based on the quadrant operation. Then based on the number of pulses, as we know, suppose if we take a semi-controlled or the full controlled rectifier. So in the semi-controlled and full controlled rectifier, or let me consider the full controlled rectifier. In full controlled rectifier, the rectifying elements, all the rectifying elements which we are using are the thyristors. So then if you want to get the function of the rectifier, we should turn on and turn off the thyristors. Of course, there is a sequence, we should follow that sequence to get DC output voltage. So in case, then the conditions to get turn on the thyristor, there are mainly two conditions. The first condition is we should give the positive anode voltage with respect to the cathode. And the second condition is we should give the gate pulse to the gate with respect to the cathode. Because without giving the gate pulse, if you give only the anode current positive with respect to the cathode, the thyristor will not get into the conduction mode. We should give the firing pulse or the triggering pulse to the gate signal, then only it will be turn on. So then how many pulses are the triggering pulses that we are giving to the thyristors? Based on that also we can classify. Like if you give only one pulse, then it is called as a one pulse rectifier. And if you are giving the two pulses, then two pulse rectifier, three, then three pulse rectifier, and then six, the six pulse rectifier. Of course, there is no 4 and 5 pulse rectifiers, only 1, 2, 3 and 6. This we will get to know when we are discussing about the different types of rectifiers. That time we will get to know. Fine. So these are the different classification of the rectifier based on different parameters. The first one is based on the input supply, and the second classification is based on the quadrant operation, and the third classification is based on the number of pulses. And next, the principle of phase control rectifier. So what is the principle behind the phase control rectifier? So as just now we discussed, to get turn on the thyristor, we should it should satisfy the two conditions. One is, you can see here, the first one, the SCR conducts only when anode voltage is positive and gate pulse is applied with respect to the cathode. Then only the thyristor will get turned on. Without giving the gate pulse, or without giving the triggering pulse, or without triggered the gate, the thyristor blocks the flow of load current, because still it is not a conduction mode, because we didn't trigger the gate pulse. So once we trigger the gate pulse, then the thyristor will start conducting, then the load current will flow. Then here, of course, just now we have discussed the basic classification, which is uncontrolled, controlled, and semi-controlled. Then what is the controlling parameter here? It is, that is the firing angle. Here the firing angle is the controlling parameter. So by changing the firing angle, we are able to change, or we are able to control the output DC voltage of the rectifier. Then how we can measure the firing angle? Like, let me draw here. The input is AC. So here it is an AC supply that we have given. Let us consider this is Vs, and then let me consider this is Ig, that is the gate signal, and this is V0. So the firing angle is nothing but, suppose if you give the pulse, or let me consider here it is 0 and this is pi, this is 2 pi. Here you can see the firing angle is measured with respect to a given reference at which the firing pulses are applied to the thyristor gate. So let me consider here, at this instant I have given the firing pulse to the thyristor, then the thyristor will start conducting, then we will get the output voltage and the current. Then the load current will start flow. Then this here, this is called as the firing angle. So the delay, how much delay we are taking to give the firing pulse or to trigger the gate signal, so that is called as the firing angle. So here, after an instant of alpha, so I have given the firing pulse to turn on the thyristor. So this period is called as the firing angle. Then the first topic that we are going to discuss is the single phase half wave controlled rectifier with R load. So this is the schematic diagram of the single phase half wave controlled rectifier. So here we have used only one thyristor, and the input is the AC supply, which we are considering as a Vs, which is equal to Vm sin omega t, and here load, which is the resistive load. Then before going to discuss about the operation, let me show you the output waveforms. So based on output, by using these output waveforms, so we can able to understand the operation of this single phase half wave controlled rectifier. So initially we are giving the supply. Okay, so as we know here, the AC voltage supply will having both the positive half cycle and the negative half cycle for the full cycle, which is 0 to 2 pi. So here we are having only one thyristor. Then initially when we start giving the supply, the input supply here, which means we are applied a positive voltage across the thyristor, which is the anode is positive with respect to the cathode. That's what we have applied. You can see here the positive and the negative. But still the thyristor is not in a conduction mode, even though if you are giving the positive voltage across the thyristor with respect to the cathode. which is anode is positive and cathode is negative. After some delay, we are giving the firing pulses. Okay, the delay angle is, we are call it as a alpha, which is the firing angle. So we are giving a pulse or trigger the thyristor. Then the thyristor starts conducting, so that we will get the output voltage and output current. And the output voltage and output current will follow the supply. Here you can see up to alpha, here there is no output voltage and output current, because still the thyristor is in the off state. When we are giving the firing angle at alpha, then the thyristor starts conducting. Then we are getting the output voltage and the current, which is followed by the source voltage. Then up to, here the commutation that is used as the line commutation, because as we know already, the line commutation, which is also called as the natural commutation, because here the nature of the AC voltage here, up to pi degrees it is the positive cycle, and after pi to 2 pi it is a negative cycle, which means automatically after the pi degrees, okay, or after the pi, the voltage across the thyristor will get reverse biased, so that the thyristor stop conducting. That's why here you can see we are getting the output voltage from alpha to pi only. But after pi, here the output voltage is 0, and as well as the output current is also 0, because the thyristor is in the off state due to the natural commutation. Then again, after 2 pi, again we are getting the positive cycle, then which is nothing but the positive voltage will apply across the thyristor, but still it is not in a conduction mode, because we didn't give the firing signal or the firing pulses. Then again after the pi, we are given the firing pulse, then again the thyristor will start conducting, then we will get the voltage, output voltage and current, which is followed by the source voltage. This is how the operation, which means during the positive off cycle, okay, here the load current will flow in this direction. This way. I naught. And during the negative off cycle, here, because during the positive off cycle, here the anode is positive and the cathode is negative, or the anode is positive with respect to the cathode. But during the negative off cycle, this will be negative and this will be positive. So which means the reverse bias applied across the thyristor, so that the thyristor will get into the off state. That's why here we are getting the output voltage and output current during the positive off cycle only. During the negative off cycle, because the thyristor is in the off state, so that we won't get the output voltage and the output current. That's why this is a single phase off wave control, which means only during the positive off cycle that we can control, but during the negative off cycle we cannot control, because we are getting the output voltage and current as 0. Right. So based on the firing angle, we can control the output voltage and current, the average or RMS output voltage and current, that we will discuss. Then how to derive the average load voltage and average load current. So as we know, because for this particular waveform, here you can see the V0 and I0 waveforms are symmetrical, are similar with each other, because here you can see Vm sin omega t, okay, and this current is Vm sin omega t by R. So because these two waveforms are followed by the input waveform, which is sine wave. So that's why as we know how to find the average value of the sine wave, which is the general formula, just I am here writing, that is, let me consider E average, which is equal to 1 by T integral 0 to T, because the sine wave that we are representing as a Vm sine omega t into d omega t. This is the general equation to find the average value of a sine wave. So here we should identify what is this t and this t. This t and this t are not same, because this t is the total time period and this t is only the conduction time period. Then first we should identify what is the total time period and what is the conduction time period. Then again, let me go for the output waveform. Here, if you see the total time period, which is 2 pi, 0 to 2 pi, because if you see, if you consider 0 to 2 pi, then again 2 pi to 4 pi, the waveform is symmetrical. Otherwise, if you consider only 0 to pi and pi to 2 pi, see here 0 to pi, you are getting some conduction period, but pi to 2 pi it is 0. So these are not symmetrical, the 0 to pi and pi to 2 pi. But if you consider 0 to 2 pi and 2 pi to 4 pi, these are symmetrical. So which means the total time period is 0 to 2 pi. Which means after every 2 pi, the thyristor will get conduct. Like here you can see, this is alpha to 2 pi plus alpha. I mean, it is first the thyristor is conducting at alpha, then after again it will conduct 2 pi plus alpha. So then the total time period is 2 pi plus alpha minus alpha, that is 2 pi plus alpha minus alpha, then which is equal to 2 pi. So then the total time period here t is equal to 2 pi. Then what about the conduction period? The conduction period is only here from alpha to pi, not 0 to pi, because from 0 to alpha there is no conduction here. You can see the output voltage and current are 0. So anyway, here we are going to find the average load voltage. So that's why we should consider only the output voltage waveform. So here from 0 to alpha, the output voltage is 0. It will start conducting from alpha to pi. So that's why here we should take this t as a 2 pi and this t as a pi, because, and here it is not from 0, because here it is from alpha to pi. The same equation you can see here, the EDC, which is equal to, because anyway the output voltage is DC, so 1 by 2 pi integral alpha to pi, because here the output, I mean the output voltage that we are getting from alpha to pi only, so alpha to pi Em sin omega t into d omega t. Then you can just apply the integral to the sin omega t, then apply the limits. Here you can see the sin omega t, which is the integral of sin omega t is minus cos omega t, and then you can substitute now the limits which are from alpha to pi, then you will get EDC is equal to Em by 2 pi into 1 plus cos alpha. This is the standard equation, so everybody should remember this one. What is the average load voltage of a single phase half wave controlled rectifier with R load, which is EDC is equal to Em by 2 pi into 1 plus cos alpha. So here if you see how we can, because as we know, as we say or as we consider, this is a half controlled rectifier or half wave controlled rectifier. So which means we can control. Okay, output can be controllable. Of course, some extent we can controllable. Then what is the key parameter here is alpha, because Em which is constant and 2 pi which is constant, only the variable is alpha. So by changing the alpha value, we can control the output voltage. We can consider, if we consider 30 degrees, then we will get some value of the, what is that, the average load voltage. And if you consider alpha is equal to 60, then the value will change. So like this we can control the output voltage. Next, the average load current. As we know already, the average load voltage. So then we can just EDC by R, then you will get average load current, which is EM by 2 pi into R into 1 plus cos alpha. So this is the average load current. Like that, we should derive the average load voltage and the average load current. So here the basic thing is, this is the basic equation. If you remember this basic equation, then you can easily solve the average load voltage and the average load current by deriving this. These are simple integration. Okay, if you just apply the simple integration and substitute the limits, then you will get the average load voltage and as well as the average load current. Then how to find the RMS load voltage? Then again from the standard equation in case of RMS voltage of a sine wave. So let me consider if it is a voltage VRMS, which is equal to again 1 by T. Here first let me go for the equation. So here 1 by T into integral, again it is from 0 to T, again here it is Vm sine omega T whole square into d omega T, and we should give the root because the root means square RMS value. This is the standard equation. Again in this case we have to identify what is the total time period and what is the conduction period. The conduction period, it is from alpha to 0 to T usually we consider, because this is a this for the sine wave. But anyway, here for the load voltage already we have identified the total time period and as well as the limits. The total time period here it is 2 pi and the limits are from alpha to pi. The same things here I have substituted. You can see 1 by 2 pi in the place of T I have substituted 2 pi, and the limits of the integral is alpha to pi, then Em sine omega T whole square into d omega T. Then again you can just simplify this equation, then we will get the RMS load voltage. Here I have taken Em square as a just because Em square is a constant, only here the integral that we can apply to the sine square omega T into d omega T. So here the sine square omega T we can write it as a 1 minus cos 2 omega T by 2. Then apply the integral for the 1 minus cos 2 omega T by 2. Then if you apply the integral, then here the integral of 1 into d omega T will become omega T, and the integral of cos 2 omega T will become sine 2 omega T by 2. Then apply or substitute the limits which are alpha and pi. Then finally you will get the ERMS, which is equal to Em into pi minus alpha by 4 pi plus sine 2 alpha by 8 pi and whole to the power of 1 by 2. This is your the standard. So this is the final RMS equation. This is also everybody should remember what is the RMS value or what is the RMS equation of the load voltage in case of single phase half wave controlled rectifier with R load. That is ERMS is equal to Em by 2 root pi into pi minus alpha plus sine 2 alpha by 2 whole to the power of 1 by 2. Similarly, we can find R, as we know here alpha is the key parameter to change the output voltage and current. So suppose if the firing angle alpha is equal to 0, then we will get the maximum RMS voltage, which is ERMS is equal to Em by 2. Because if you substitute alpha is equal to 0, okay, then here the pi gets cancelled. Then here alpha is 0, okay, and sine 0 is equal to 0. So 0 by something 0. Then the total term inside the square root, okay, will be having only the root pi. Then the root pi will get cancelled. Then we will be get, because here you can see this term will be get 0 and this term will be get 0, and here this term will become root pi and the root pi will get cancelled. Then you will get only Em by 2. Like that, the RMS value will depends on the alpha value. Then the RMS load current, similarly like RMS load voltage, already we know what is RMS load voltage. Then just ERMS by R, then you will get the RMS load current. Okay, so that's how we can derive the RMS the average load voltage and current as well as the RMS load voltage and current. Next, the power delivered to the load. So there is a DC and AC powers. The input is AC power and output is the DC power. So suppose if you want to find the PDC, then it is EDC into I. Already we know what is EDC and IDC. Just now we have derived. Then you can substitute EDC and IDC here. Then you will get the PDC. And similarly PAC, that is RMS load voltage into RMS load current. Okay, so just now we have derived the RMS load voltage and current. You can just substitute the ERMS and IRMS. Then you will get the PAC, that is IM square IRMS square into R. So similarly, the input VA, that is RMS source voltage into total RMS line current. Okay, then you can substitute these two values. Then you will get the total input VA, which is root 2 into ES square by 2 into R into root pi into pi minus alpha plus 1 by 2 sine 2 alpha whole square. And we can also find the power factor by using this equation, because these all are the standard equation that you know already. These are all the parameters like the power delivered to the load and input VA and the power factor. If you want to find all these parameters, before that you should find the average load voltage and current as well as the RMS load voltage and current. Then the power factor, which is equal to, if you substitute the power delivered to the load and input VA, then you will get the power factor which is equal to ERMS by ES, because here IRMS will get cancelled, then you will get ERMS by E. This is the power factor in case of the single phase half wave controlled rectifier with R load. Similarly, we can also, or if you substitute the ERMS and ES value, then you will get the final equation for the power factor, which is this one. Then the efficiency PDC by PAC, that is output by input. Here output is PDC and input is PAC. So just now we have here calculated, this is PDC and this is PAC. Then you can substitute, then you will get the efficiency. Similarly, the ripple factor, that is ERMS by EDC. Okay, so like that we can find the different parameters based on the average load voltage and current as well as the RMS load voltage and current. This is how we can find. So this procedure, whatever the procedure we have followed to find the average load voltage current and as well as the RMS load voltage and current, the same procedure that we can follow for other types of rectifiers also. Like next we are going to discuss about the single phase half controlled rectifier with RL load. So for the RL load also the same procedure. Here the key parameters are that we have to identify what is the total time period and as well as what is the conduction period. These are the only the two key parameters. So based on these two key parameters, so we can derive the average load voltage current as well as the RMS load voltage and current. Next, the single phase half wave rectifier with RL load. See, then when coming to the output waveform, just you have to compare with the single phase half wave rectifier with R load. Okay, so which means here we should find what is the effect of these inductance or effect of this inductor. If you see the output waveform, of course the procedure is same, the operating procedure, right? So here initially we are giving the positive anode voltage with respect to the cathode, and at alpha or after firing at alpha degrees we are giving the firing pulses to the thyristor, then the thyristor will get turned on. But before, as you can see here, in case of R load, the output voltage waveform is this is 0, pi, 2 pi, like this we got the output voltage waveform, and as well as the current also we got same waveform, similar like the output voltage. So which means when the thyristor will get turned on at alpha degrees, so the current is rising very rapidly and it is following the the input voltage or input waveform. But in case of RL load, here you can see when the thyristor is turned on, still the current is 0 and it is gradually increasing. Okay, and even though at pi, okay, still the current is flowing through the load, but it becomes 0 when it reaches to the beta. Why here it is not rise rapidly like in case of R load? Because here the basic property of the inductor. The basic property of the inductor is it does not allow sudden change in the current. So that's why here it is gradually increasing, okay, and after it reaches to the peak value, then it is gradually decreasing and it will become 0 at beta. Then when coming to the load voltage waveform, anyway from alpha to pi it is similar to the voltage waveform which we got in case of R load, but here we are getting a small amount of negative voltage from pi to beta, because this is initially when we are giving the firing angle alpha, then the current will flow in this direction. So which means then the inductor terminals are like this, plus and minus. So during the thyristor T1 is conducting, the inductor will store the energy. So when the thyristor terminal will get reverse, then here the inductor will start to discharge by changing its terminals as a negative and positive. Then it will discharge through the it will discharge the energy, but still in this case also the thyristor will get into the turn on position. So that's why here we are getting some load current from alpha to beta. Okay, so then in this case the conduction period is alpha to beta, not alpha to pi, because even though some some duration from pi to beta, still the thyristor is in the conduction mode. When it reaches to the beta, then the thyristor will stop conducting. Then the load voltage and the current will become 0. That's what here you can see by this VT. This is the terminal voltage across the thyristor. So from 0 to alpha, thyristor is in the off state. So that's why we are having a small voltage across the thyristor. And again here from alpha to beta, so there is no voltage across the thyristor because it is in a conduction mode. So that's why here the voltage across the thyristor will become 0. Then after beta, again the voltage across the thyristor will follow the same source voltage which we are applying. This is the operation of the single phase half wave rectifier with R load. So then this is the effect of the inductance in the load. We are getting a small negative voltage, and as well as we are getting the conduction period also increased, because before it was 0 to pi, alpha to pi, but here it is alpha to beta. Then here you can see there are 3 different angles. One is alpha and beta and gamma. So here already we know alpha is the firing angle, and here the beta is called as a extension angle, because the conduction period is extended from pi to beta. That is, the beta is called as a extension angle, and then the gamma is called as the conduction angle. The gamma here you can see from alpha to beta, the duration is called as a gamma. So that is the conduction angle. And the extension angle is not from pi to beta. Okay, that you should observe here, from 0 to beta. This is called as a extension angle. This duration is called extension angle. And alpha is only this duration from 0 to up to this point. This is the firing angle. Then in this case also, we can derive the average load voltage and the average load current. Similarly, here the same equation we are using, but only the change is here the conduction time. The conduction time in this case is alpha to beta, and here the total time period again 2 pi, similar like in case of R load. Then apply the integral, then substitute the limits, then you will get EDC is equal to Em by 2 pi into cos alpha minus cos beta. Before it was Em by 2 pi into 1 plus cos alpha. Here it is Em by 2 pi into cos alpha minus cos beta. That's what here the output load voltage will also change with respect to the load also. Then similarly, the average load current, already we derived the average load voltage, then EDC by R, then you will get the average load current. Similarly, the RMS load voltage, here the same equation, you can just apply the integral and substitute the limits, then you will get the RMS load voltage, which is equal to Em by 2 pi into beta minus alpha minus 1 by 2 into sine 2 beta minus sine 2 alpha whole square. The similar way you can also find the efficiency and as well as the power factor, okay, and as well as the ripple factor, similar like in the previous case. The basic thing is you have to find the RMS load voltage and RMS load current. The next topic is the same half wave rectifier with RL load and freewheeling diode. So what is the effect of freewheeling diode, that we will discuss in the next class, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.